Hi folks, we're going to take a look at page 435, numbers 1 and 2. So here we're given these three functions, or the graphs of these three functions, and we're being asked what combination, when we multiply them, will give us an even and odd function. Okay, so I'm going to do this in two ways. I'm going to do it by just essentially observing the graph, and then I'm going to do it in a more analytical way, which I would say is the better way of solving this problem. So one thing that we notice is that function A is even, function B is even, and function C is odd. Okay, so again, if we just do this by observing the graph, let's say here we compare any x value with its negative counterpart. So let's say we take 2 and negative 2. Well, we know that because A is even, these two y values are the same, and the same thing occurs with the two y values in function B. Okay, so if I multiply these two numbers, so this looks like it's about, this looks like it's negative a half, this looks like it's 2, so 2 times negative a half, I get negative 1. And then when I multiply these same two y values at x equals negative 2, I again have 2 times negative a half, okay, which is negative 1. So in the end, I can see that no matter what x value I pick, when I multiply the two y values at the positive version and at the negative version, I should come up with the same result. So that tells me that A times B should be an even function. Okay, now if I take function C and I compare it to, say, function A, okay, we see that something similar happens. So let's say I take x equals 1 and negative 1. I see that when I multiply the positive versions, positive 1 times positive a half, the two y values at 1, I get a half. But when I go to negative 1, I have 1 times negative a half, which is negative half. So we see that when I look on either side of the y-axis, those two y values, when I multiply, will be negatives of each other. Okay, hence this product of an even and odd function is going to give me an odd function, and I can make a similar argument, okay, using this even function and that odd function. Okay, the last thing they ask us to consider is what about when we multiply all three? Okay, now we've sort of already done the work for that, because I know that if I multiply A and B, two even functions, I get an even function, and then when I multiply an even function and an odd function, I'm going to get an odd function. So the product of all three should just be an odd function. Okay, but let's try to do this now in a more analytical way. Okay, so let's remind ourselves what it means to be even or odd. So A and B are even. It means that if I apply A to negative x, it should be exactly the same as A of x. B applied at negative x should be the same as B of x, whereas for an odd function, which is C, C at negative x is the negative of C at x. Okay, so if I pick, say, a combination and I want to look at the function AB, okay, I want to evaluate the function AB at negative x and see how it compares to AB evaluated at x. So here I use the definition of the product of two functions. So this is the same as A at negative x times B at negative x. Okay, and because A is odd, I know this is equal to A at x, and A is even, so it's equal to A at x, and B is also even, so this is also equal to B at x. Okay, and I can rewrite this product as AB evaluated at x. So what we've shown is AB at negative x is equal to AB at x. In other words, okay, AB is even. Okay, now I can take any one of these. So let's say I take A and C. Okay, A, C. And again, I want to evaluate this at negative x and see how it compares to AC evaluated at positive x. Okay, so here again, I apply the definition of a product. So this becomes A at negative x times C at negative x. A is even, so this is equal to A at x. But C is odd, so this is negative C at x. So I'll just rewrite this. Negative A at x, C at x. Okay, and these two expressions multiplied here is the same as AC at x. So we see that AC evaluated at negative x is the negative of AC evaluated at x. Therefore, AC is odd. Okay, and I can make the same argument for B times C. I won't do that because it's exactly the same. So lastly, let's show that ABC is also an odd function. So I'm going to take this function and evaluate it at negative x. Okay, by the definition of products of functions, this is the same as A at negative x times B at negative x times C at negative x. And again, A is even, so equal to A at x. B is even, equal to B at x. And C is odd, so equal to negative C at x. And again, as I did before, just rewrite this with the negative in front. Okay, and this trio here can be rewritten as, oops, that should just be a negative A, B, C at x. So we see ABC evaluated at negative x is equal to the negative of ABC evaluated at x. Therefore, ABC is an odd function. Okay, so there you have it. I would say that this second version is the more analytical way of solving the problem, but you can make a graphical argument by comparing x values to the right and left of the y-axis. Okay, that's it for this one.